Kimi K3 came out a couple weeks ago on API only, and people were starting to experiment with the API, and also this blog post came out, and people were just blown away because this is the first open source model or open weights model that's made it into this sort of class of the frontier, essentially, where if you're looking at some of these coding benchmarks, like it's trading blows with 5.6 Sol. It's right up there almost with Fable on some of these. And some of them, Program Bench, for example, it beats Sol and Fable 5. So people were saying, hey, this is incredible. Like, let's try out this model. And if you look at some of the, like, it pushes up not only just the capability frontier, but they're able to do it in a way that it pushes up the efficiency frontier as well. If you look at the cost for some of these things. Now, in the meantime, it's sort of in the intervening time after this model came out, OpenAI has lowered some of their prices and has made some of their models a little bit more competitive. Not necessarily at this capability level, but like at the lower capability levels, making this a little bit less unique. But we'll talk about it later, where some of these open source models are also pushing up that frontier as well. But the cool thing is that, first of all, this is also a very large model. It's a 2.8 trillion parameter model, which is just a lot of weights. That you have to have such a large computer to be able to run this. I mean, we're not talking about a single machine anymore. We're talking about, a rack of, B200s, B300s. You have to have the latest of the NVIDIA technology or the latest of the AMD. You're basically talking at about $500,000 in terms of just buying the server that needs to run this. But if you do have that server, you can run this completely on your own without accessing any third-party service, without paying any money to Anthropic or OpenAI or Google, or XAI. You're not paying anybody. You could just run this yourself for your own purposes. And so that's a massive sort of jump in freedom that you get from just having access to this model. And it's a relatively permissively licensed model. They do have some terms in their license that say if you're going to serve it to others, if you're going to serve this as a service, as an API service, you have to basically go to them for an agreement. And we can talk a little bit about what might be some of the terms of that agreement. One of the things you kind of hear is that GPT-3, that model, got so much stuff right, and the attention mechanism in that model got so much stuff right, that what we're seeing today is just kind of scaled up versions of those. And that is still true, that at its core, these models are kind of just variants and different implementations of that. But as we start to get into this latest versions of these models, they are starting to do things that reinvent in some ways what the attention mechanism looks like. And so it's not so simple anymore as just a multi-layer attention head. Like, we've got these more efficient mechanisms. Like in this case, KDA is this Kimi delta attention, where it's a different formulation, and they're kind of strobing in between this Kimi delta attention and the full weight attention. And then we've got these other variants as well. So this is no longer just the standard attention mechanism scaled up. They're doing some interesting things with the architecture here. And we've got all the different model providers that are kind of doing variants on this. They're all co-evolving in similar directions. Like if you look at Qwen, they have something called gated delta net. And this is relatively similar in a lot of ways. DeepSeek sparse attention. These are similar mechanisms where we're trying to take what happens when attention grows normally with normal old school implementations. It grows quadratically. So for every token you add all the computation of all the previous tokens plus the new one, which means that it just keeps getting more and more. At some point, you hit a limit where you can't inference very fast. And so some of these adaptations of the standard attention mechanism make this possible. And if you look at the results on coding, on GPU compiler development, so this is like kernel development. Some of these things, it really reaches state of the art. So this is cool. I mean, if you just look at the numbers of their own benchmarks and what people have benchmarked out there. These are real, and like these are really impressive artifacts that it's creating. So now, what I was talking about before was it was released under the API. It was released under the SDK. When we first got this blog post and we were reading through it, everyone was excited. People were using the SDK, people were using the API, but there was a big question about, are they going to actually release this as an open source model where anyone can download it? Well, I'm happy to say that as of today, as of a couple days ago, this was released as open source. You can download it. You can look at the files. These safe tensors, these are the actual weights you can download. It's a lot of files. It's a lot of weight. But you could run this on your own cluster if you want. And what's cool is to see the exact specification of it. Is they've changed a lot from Kimi K2.5 and Kimi K2 to Kimi K3. It's a lot bigger. There's a lot more. So there's 2.8 trillion parameters total, and now we're activating 104 billion parameters every forward pass. There's a lot more layers. Let's go to the white paper. This is not an artifact that we get anymore from Frontier Labs. When you look at OpenAI and when you look at Anthropic especially, they are not going to release this type of information. And as we'll see, as we go through this, there is a ton of great information. So let's go through just some of the interesting bits. So this talks a little bit more about their stable latent MOE. So this is like, how are they stabilizing in the early days of language models? We used to use something called dense models, where every single weight gets read and activated for every single forward pass through the model. And as we have scaled these models up, we've realized that you don't really need every single weight to be activated in every single forward pass. You can sort of, on every single layer, you can select a subset of the weights that you know will be relevant to this query. And they call that a mixture of experts. And one of the problems with mixtures of experts is that they're hard to stabilize. They're hard to train. Why would they be hard to train? You can imagine, just think about like, okay, if you've got 8 different people that you could call on to help, and you know that you've gotten a good answer from, person A, and they answered you really well before. They did a great job. And for all these other ones, they haven't done as good of a job. You're going to constantly get, if you want the most reward, if you want the best sort of output, you're going to constantly give it back to that first person. And that's not necessarily what you want to do, because if you just do that for your entire training, then that one route is going to get all the traffic, and none of the other routes are going to get the traffic. They will never get better. They'll never improve it at answering your question. And then there's going to be just all the data is going to go towards that one person. And then that one person, yes, they'll be good, but they'll have to be good at everything. They won't be able to specialize in anything. They will get overloaded by all these requests. And then there's 7 people basically just sitting there doing nothing. So with mixtures of experts, there's all these different mechanisms for trying to stabilize the training and say, okay, even though you know that you're going to get a worse answer from these people, you have to spread out the work, and then they learn, they get better, and you can even it out across them. So that's like the mental way of thinking about it. We can dive in a little bit, but they've got some stabilization techniques that they use here. But yeah, so the model architecture, they talk about this is this new Kimi delta attention strobed with gated MLA. So it's not all Kimi delta attention. It's not all gated MLA. It's like it's going back and forth between them. And then there's a really cool thing here called attention residuals, which we'll talk about a little bit later. But it's, I think, one of the more interesting developments of this model in general. I don't think that we've seen attention residuals on any public model as large as this one. There has been a question about whether attention residual scales, and this model answers that question in the affirmative, that yes, attention residuals scale up, and they're useful. You might ask, why are we switching to this KDA in some case? Why not just do the standard full attention for everything? And this is actually a reasonably good description of why. So you can imagine that if you have to compute all of these boxes equally, it's going to take more compute than if you only have to compute this diagonal sometimes, and then only every once in a while activate the entire triangle. That's kind of just like a visual representation of the difference between, like, what this is doing is linear attention, and what this is doing is that quadratic attention. And there's different way, like they've got different ways of making this efficient. This is a great table that just compares Kimi K2 and Kimi K3. Kimi K2 was a 1 trillion parameter model. Kimi K3 is a 3 trillion parameter model. The previous version had 61 layers, and the current Kimi K3 has 93 layers. And in a lot of ways, I think that depth represents intelligence capacity. Like, it's true that width and depth can kind of be interchanged, but we do see in small models that if you expand the depth beyond the width and you push on depth, you can get to certain algorithmic outcomes that you can't get with a smaller one. So while I think width and depth can be interchanged, I think depth is the one that, for a very small class of problems, depth is the only thing that can unlock it. So whenever depth increases, I think that's a pretty good sign. We're also, like I said, the last model was only activating 32 billion parameters. The new model is activating 104 billion parameters every pass. So that's a lot. That's a lot more. Same hidden dimension size, pretty much. More hidden dimensions per expert. This is going to make it better, easier to route between experts, and better, more accurate routing between experts. It's going to more often send it to the right expert. And there's a lot more experts. Before there was 384, now there's 896. And activating 16 per token. We're also increasing the attention heads. If you look at like the standardized attention model, you have a variable number of how many heads you want to activate. And this is a pretty big number. This is a pretty important number to iterate on. Anyway, so they're switching between their attention mechanisms, where it used to just be MLA. Now it's this hybrid between KDA and MLA. They also switched. They found that Swiglu, which is kind of like the standard activation function, they found that there were some outliers. Like, these numbers didn't have bounds on them, and they created this sort of modification of it that bounds the numbers. And yeah, I was talking about how there's like, it used to just be MLA. Now they have it spelled out where some of it's MLA and some of it's KDA. Kimi K3 trained with a whole lot less flops than Kimi K2. So that means that even with all of these increased numbers here, we're still, for the same amount of time, going to get to a better performance. So that's why Kimi K3 is better. It's a stronger model overall. It came out better in pre-training, and it post-trained better as well. And that a lot of that is just due to the fact that it's faster. It's faster to run through all these forward passes. And so they go through their training recipe. I don't think we need to talk about this. This is pretty standard. Oh, one thing that's kind of cool is they don't use positional encoding. When I think about the fact that you can just not positionally embed your tokens, that means your model doesn't know which order all the letters come in or the subwords come in. The tokens that are coming in don't have an order that they're given. So it sees the whole bag of your request as one big long bag, which is crazy that works. It turns out the model doesn't need them. It just can see all the different tokens you put in. It can figure out the order on its own, and it can reason about it, and it doesn't need all those. It doesn't need a positional encoding. Crazy to me, but true. They trained their own agentic generative reward model. They trained 3 different models. They trained one that was just good at general tasks, general experience, vision, reasoning, faithfulness, search capabilities, and knowledge and work tasks. So their first fine-tune they used reinforcement learning for was just general tasks. And I think this was probably just meant to be like a really task-based thing. Like, I have this thing I want to be done. I don't really care about how you accomplish it, but in the end, this needs to happen, or this observation needs to be had. That you need to have done some search to get some data, and you can only get to this answer if you've done that, for example. Then it looks like general. I don't actually know what the difference is between general tasks and general agents. I guess tasks is probably more one shot, and general agents is probably more, I guess, long horizon. Okay, deep research, paragraph level writing. And then the third one is coding agents, which you can imagine is like it has to learn about all the coding languages that people would want to use. It has to have specialized knowledge in something like kernel development, web development, things like that. So they trained these three different models: general tasks, general agents, and coding agents. And they say that and you can see that like as they scale RL, they just get better and better at all these things, right? In their generative reward model, they first have like the model assess the rollout, generate a rubric for it, and then score against the rubric, which is kind of cool. But okay, so once we've got these three models, the general tasks, general agents, and coding agents, they do something called multi-teacher on-policy distillation. And actually, the first time I really saw this formulation, this multi-teacher on-policy distillation, was in the DeepSeek V4 paper end of last year, where they do a very similar thing. And I think what's happened is that everybody's converged onto this. On-policy distillation says, so okay, each three of these models started from a base. You've done pre-training, you've done some amount of post-training, and then you have this like generic base model that you start with, mid-training, post-training. You have a generic base model. And so from that base model, they created this tasks, agents, and coding, right? You go back to the same model that you started with. And with RL, when we're talking about these RL stuff, it has to generate an entire sequence of tool calls and do a lot of inference until it gets to what it thinks is the answer. And then it says, here's my answer. Yes or no. Is this good or bad? Or maybe give me a number about how good or how bad this is. But in the end, you do all of this work, and then at the very end, you get one number back. And so it's very inefficient. You can think about this as like being limited by our inference speed. How fast can we run these forward passes? How fast can we like run these agent rollouts? But once you get to these three specialist models, you have experts. You have three experts that are really, really good at these things, right? And so you go back and you start from the same base model that you started all these experts before you trained them. You give prompts to this. So you generic prompts that span everything that you want to do. And you give it the prompt. It doesn't just output the next token. It outputs a probability over all the possible next tokens. And so you take the probability across all next tokens and you present it to each expert. And you can basically use a mathematical formula to say, okay, how much does each expert and how confidently does each expert agree with the distribution that you've put out? And you can basically take all those experts and distill it and say, okay, between all these three, this expert and that expert are very confident, and they say that, you know, it doesn't, you should nudge your distribution slightly this way. And so as for RL training, you have to do all these tokens for a rollout. When you're doing this expert distillation back using on-policy distillation, every single token that it outputs gets scored by all three experts. And so it's a very quick way of taking these like super specialized experts and sort of merging it into the base model in a way where they're all working together. You don't have three experts anymore. You have one model that's really good at everything. And by doing it on policy like this, by taking its model's own outputs and scoring it, you're always improving the policy as it exists in that base model. There a lot of older formulations did off policy distillation, where they would sort of like, this is a good example, this is a bad example, like take that and nudge your policy in that direction. But oftentimes the good and the bad example were both not something that the base model would have put out. So it's kind of just like shifting it around in a space that doesn't make sense. But with on-policy distillation, every token that the model outputs gets scored across three experts or five experts, however many experts, but in this case, it looks like three. And then, so it's a very, very, very dense training signal. And the GLM 5.2 paper said that they can do the on-policy distillation in 2 days on their cluster. So it's a very dense signal. It's a very quick step in this process, but it's very powerful because you're taking these experts and you're sort of merging them, and so you're getting a powerful model at the end. So that's kind of cool. Seems like they did quantization aware fine tuning, where they're using basically efficient fine tuning, where they're using lower bits for certain parts of the model. That's pretty cool. Then they go into a lot of detail about their various different RL environments that they have set up. So, like, they categorize it into these various different types of tasks, where you might do coding, you might do chemistry, you might have a math thing, and they synthesize all these different tasks. Research and knowledge graph construction are good tasks. They also specifically implement kernel optimization, which means that the model is getting better at writing code that the model itself will use, because kernel, a lot of times the limiting factor on how fast your inference can go is how good your kernels are. How well are you taking advantage of the GPUs that you have? If you've got bad kernels, you're going to be using those GPUs inefficiently. If you've got really good kernels, you're going to be using them more efficiently. And as we've seen in the earlier parts of this paper, as fast as you can inference is as fast as you can train, and so it just makes that a lot better. It looks like they've also created mock implementations of Gmail, Notion, Slack, and Canvas. Like, this starts to get into this, like, if all of a sudden you notice your model gets way better at doing Gmail, well, it could be because they simulated it. They created an entire simulated version of Gmail and then taught the model to interact with it. And so you'll see this on like things like Slack, or if all of a sudden one of your use cases gets a lot better, it's highly likely that the model company built some environment like this. And in fact, web development, we'll talk about it soon, but Kimi K3 has some of the best scores of any model anywhere on web development stuff. So that's pretty cool. And you can tell that a lot of this is based on their curated web development tasks that they've built and the rubrics that they've got for training against it. They talk about they talk about their context parallelism and how they're able to split things off into different compute loads that can happen at the same time and then combine, and how they can figure that out using the like attention patterns. This is like where it starts to get just super cool and insane, is that sort of because these things are disaggregated, they're distributed across different nodes, you have to be really clever about sort of, okay, I've started some work on here from this part, and it has to transfer over the network or transfer to another device, and that other device is going to run another pass on it or do another thing on it. And we can't do anything until with that piece of data until it's been transformed or done something in the other part of the architecture. And so you can kind of trace like the number one through here. And this is like one piece of data where you're gonna be very careful about what you're doing when, and you're not going to just only compute basically the number one data, because if you just compute the number one thing and then just wait for it to be done, you're going to be waiting until like basically over here. The idea is that by carefully selecting which order you're working on, what operations, you can basically multiplex and create a situation where you're never waiting. The only time when any of these GPUs are waiting is in these blank spots. And that's what we're trying to minimize, is these number of blank spots where you're doing nothing. And using this particular setup that they've figured out, that's a very, very efficient workload where it's really not pausing very much at all. There's very few bubbles in the pipeline. We talked about balancing MOEs and how it can be difficult, but they found some stuff. They created this MoonEP, and MoonEP actually has open source component where if you look at this, you can see this is a massively improved algorithm compared to DeepSeek's version. And I think a lot of people are going to switch over to this right away. For LLMs, maybe you had like we had convolutional neural nets, and we were doing things like image detection, image segmentation. So is this a bird or is this a cat? Something like that. And you would run your forward pass through all of these different like convolutions, and you'd say, I'll do a convolution here, I'll do a convolution there, I'll do, and every single layer was like a convolutional layer. So the difference between that model and the current model is that you see all of these like these lines along the outside. Why do those exist? Well, those are called residuals. If you look down here, we talk about this later, where how many layers do they have? The old Kimi K2 had 61 and Kimi K3 has 93. There's no way that we could get 93 layers by just passing it from layer to layer. You pass the output of one layer to the input of the next layer, you pass the output of that layer to the input of the next layer. If you just did that the whole way through, what happens is you get something called the vanishing or the exploding gradient problem, where at some point the signal gets lost. Some layer is either mistrained or activates in some certain way that just like either sends a number to zero and then multiplying by zero by like you keep multiplying zero by anything and you get zero. And so you can imagine like whenever anything goes to zero, everything else in the chain is going to go to zero. You can do a lot of tricks where you sort of try and prevent it from ever hitting zero or ever hitting infinity, or you prevent it from the edges. But the problem remains the same, which is that this original sort of input that came in at the beginning, it has to pass through so many layers that it's hard to keep it intact. And so what happened was Microsoft came up with this idea called ResNet. And it was really popular as soon as it came out because it just helped so much. And what is ResNet? ResNet is the concept of like taking the original weights, like the original signal, and just passing it through. So that there's like a superhighway of information that goes through all of these. And there's always a signal coming from that very first model or from that very first thing, and is added at every layer. And so this has been basically the way that everything has worked since then. Everything has done this. They added it in ResNet, and then when Transformers came out, it was just a pretty much a constant part of the Transformer network, where you've got this signal that's going from the very beginning, and then each time it just gets added a little, added in. So the problem with that is that it's still got a bottleneck where the previous output of the previous latent kind of needs to be routed through to the next one, and the previous output needs to be routed to the next one. And so while it is like a superhighway, it still does kind of like lose some of its predictive power, and it loses some of its signal, as well as every single layer might kind of like do a slightly different thing with that original. It might want to do a slightly different thing. So maybe it's looking for a specific feature. Maybe it's looking for a specific, I don't know, piece of information that, you know, we don't exactly know what these layers do yet. But what people started to realize is that those layers, like each one of these is kind of its own interesting view of that original residual, that original thing that came through. At each layer that some feature gets trained to look for it, it would be nice if, for example, we could look at all of the previous residuals, like every single activation. And so what attention residuals does is say, okay, let's bring that all of the previous residuals. So for a layer like for a 96 layer thing, each one would be looking at like a mix of all 96 layers and learning which one is most interesting for this one. So instead of looking at one superhighway, you're looking at a superhighway that just expands out, where each further layer gets to see all the previous layers. Problem with that, like standard attention residuals, is that you can imagine it starts to get really prohibitively expensive, especially in a distributed system like this. If something in one of these later layers needs access to like a bunch of information from the earlier layers and it can't be sort of passed along, then we've got a big problem. The idea is that instead of having it look at all the previous outputs, we're grouping them up in these blocks. And then you're computing for an entire block, how interesting is that? And that's how it can all be combined before it's used in the actual residual. This is just a way of making it so that it's possible to be computed in the budgets that we have on these forward passes and things like that. I think it would probably be better if we had full attention residuals, but the block attention residual is like a really good way of making it computable in our time, like in tight timelines. Anyway, they go into a bunch more about how they create their evaluations, cybersecurity, all these other things. I think at this point I'm going to stop reading the paper, but I just want to call attention to the idea that like it's so nice to get this paper and see all the different things they tried and see the details, looking at specifics about all these little choices that a model provider has to make when they're training their model and when they're inferencing. One of the things that I said earlier was that if the model license is not exactly, it's a permissive model license, but it's not a standard model license. One of the things that they said in this model license is that if you want to serve it over an API and charge for that API, you need to come to us and we will provide, we'll come to a deal, and you have to come to an agreement with them before they license it to you. And one of the things that's been pretty clear about this deal is that you're not allowed to undercut them. It used to be that just everything was 315, 315, 315. It seems like some people are going up, people are raising their prices. So the fast version of Fireworks is charging more. You can't make the price less. So that's interesting. That changes the dynamics a little bit. If they're saying that basically there's an MSRP on this and you can't go below that, it means it sets a price floor on it for everybody. And I think there's some really good aspects to this. It means that the developer of the model can sort of recoup some of their money, even in some of their deals with these companies. I don't know what those deals look like, but I'm assuming there could be a financial component to that. But in another part of it is that they're able to set this price floor and say that we're not going to like do a race to the bottom here on our prices. It remains to be seen whether the market bears that. But I think it's just an interesting aspect to talk about. I think I'm a little conflicted on the whole concept because I do think that these model providers should have a way of recouping their investment. Clearly, there needs to be something for that. Well, in this case, these providers do not train on prompts. In general, I've turned off routability on the ones that I don't trust. And a lot of the reason why I wouldn't trust it is that oftentimes these providers will not provide an option that doesn't train on prompts and doesn't retain prompt data. In this case of this model, it looks like there are a lot of these providers that I generally don't trust that are providing zero data rate. There is immense value for being able to capture these traces. And I think we should know the terms of these deals. Like that helps us reason about whether or not to use this model. So what's cool is that Moonshot is actually collating this list of, if you look here, this Kimi vendor verifier. They're providing a list of different providers and how they score on various different benchmarks. The idea is that like sometimes, like for example, if you have a model provider that is that has misconfiguration of their inference stack, or let's say they're trying to save money and provide you with something that seems similar or it has the same name on the tin, but underneath it's actually, quantized or they've done something to it. This is a way for you to sort of track that and say, okay, it looks like in these studies, they're all kind of configured properly, at least according to them. But I think this is a cool way that things are going, where you've got this model provider that's sort of running evaluations and checking the performance of all the different inference providers. The model provider and the inference provider when they're the same, they can kind of optimize their own stack together. But when they're different, you need some sort of coordination mechanism for figuring out like, hey, ours is like, don't use the DigitalOcean one because it's misconfigured or something. Wait until they figure out their configuration issues, or wait until they stop quantizing their model, or whatever it ends up being. In this case, everybody seems to be acting admirably, but in the past, we've seen a lot of problems with this. So I welcome this. But the main thing, one of the big things that has been exciting about this model K3 is that it's really good at front end stuff. When it comes to code, when it came out, it was the top. It was by far at the top of the model. Now, I actually checked, and it's no longer the top of the model. It's second highest. 1676 was it before, 1679. So it's dropped by just a few points. But Claude Opus 5 at max has now surpassed it. It's at 1705. So that's not Fable, by the way. That's Opus, which is kind of interesting. But Opus has had further training. The more efficient your inference stack is, and the more you can sort of run through, the better your performance is going to be. And this, like in this case, lower is better. And if we look at this, I think that's probably similar to why Opus 5 is getting a little bit further along, because it's faster to train it, and so they can run their RL on it just a little bit faster than they can. Also, Fable has been around for a while. There's no 5.1 yet. So that makes sense as to why Opus could have outperformed Fable on this. Opus is newer. It's gone through more post-training, and it's faster for it to post-train than Fable, probably. We don't exactly know all these things, but that is why it could make sense. But Kimi K3, with an incredibly impressive showing that open source can absolutely compete. And even at the price levels, it can absolutely compete. And that's it. So K3 has been an impressive model. I've actually been using it quite a bit, and we can use it more today when we do some of our neural column work. But I feel that K3 was a big moment in open source because it meant that open source finally approached the frontier. And once open source approaches the frontier, it makes all kinds of considerations change. It means that potentially you could liberate yourself from ever paying one of these companies again, theoretically. You have to spend $500,000 to get the resources to do it, and you still won't be inferencing as fast as you could on some of the shared infrastructure of a scaled provider. But this is an absolute game changer in a lot of ways. So K3 pushes up the capability sort of front. And the next model that I want to talk about is Thinking Machine's Inkling-Small. So what is Inkling-Small? Inkling came out a month or two ago, and Inkling, I think we've got a blog post here, July 15th, just 1 month ago, or a month and a half ago. Actually, half a month ago. This world moves so fast. But this was their first open source model from Thinking Machines, and when it came out, it was reasonably impressive. Like, it actually performed quite well on a lot of the different evaluations, and it's not a insanely large model. It is a 1 trillion parameter model with 41 billion active. And so we were talking about Kimi K3 before, which had 3 trillion parameters with 100 or so billion active. This is 1/3 of the size, basically, in all fronts. So it doesn't beat K3, but it does sort of hang up there with GLM-5.2. It hangs up there with these other models. It doesn't hang up there with Sol. It doesn't hang up there with Fable. But like, compared to the previous open source models, it absolutely hangs up in that weight class. So they had promised in this blog post to release Inkling-Small soon. And small one was even smaller. This is a trillion parameter model, which is not, again, K3 is larger. It's 3 times larger, but this is also not a small model. A trillion parameter model is quite large. You still need a very, very powerful set of GPUs to run that. So what about Inkling-Small? Look at the difference. Inkling-Small comes out and they say, hey, look, if you consider 975 billion parameters, this new model is a lot smaller. Not only are there fewer parameters total, but the number of active parameters are way smaller still. So whereas with the K3 we were at over 100 billion parameters active, this is only 12. So we're activating, and this is these dark numbers are the ones that really are your limiting, are the ones that limit your performance. If you have like all of them are dark, where all of them are active, it's not a mixture of expert, it's dense, it's going to be very, very, very slow. So the sparseness of this is one of the things that really contributes to its speed. And so they talk about, okay, it's been trained on NVIDIA chips. It's 276 billion parameters with 12 billion active. And look at this. It beats the performance of Inkling. It's literally better. This is the small one. It's getting better performance. And it's using a lot less flops to do so. So the bottom row is the compute that's used, and the top row is the performance, like the output quality. So at its lowest performance level, so if you look at if you look at the matched configuration wise, the lowest performance setting of Inkling-Small does worse than the lowest performing setting of Inkling. But as you scale the different thinking levels, once you get to this X high level, which would be the second one down, we're beating it. The smaller model is beating the larger model. So that's been incredible to see. If you look at the capabilities between Inkling and Inkling-Small, this makes sense to me, where Inkling is doing better at factuality. It knows more things. It knows more facts. It has a bigger set of weights to hold more, basically, the world knowledge inside of it. But when it comes to things like interpreting vision, doing chat tasks, reasoning, writing code, look at Inkling. The Inkling-Small, you can see it's actually doing a little better in the code writing ability. And I think this goes back to what I said before about the how inference performance affects your training capability. And if you can run more tokens through it, you can run more training runs, you can run more trajectories, you can hill climb faster. And so with the same amount of budget, you can get higher on the charts than you can with a smaller model, at the cost of factuality, at the cost of world knowledge. And so I think what I'm really interested in seeing is how small can we make these models? How far can we push this concept of, like, what if your factuality goes down to like 0? What if you push it all the way down? But maybe you can get like a very tiny model that still retains a lot of these reasoning and a lot of these coding and agentic abilities. That would be really cool. Yeah, we could talk more about, more evals, multimodality. Remember, Inkling-Small not only has image capabilities, but it also has audio. They've been training it with audio. It hangs up there with like Gemini 3.5 Flash Lite. It's right up there. It's way better at audio because it's actually been trained on audio samples. And on Voice Bench, MMAU, these are all audio tests. It seems to hang up there with the best. In fact, Audio MC, it's better than all the rest. It's an incredibly impressive model for its size, I have to say. They've even pushed on safety as well. So this is actually another open source model. We have it's launched, it's available on Hugging Face, so you can download the weights today. And this is Apache 2, which is one of the most permissive licenses that's available. So the idea is that you don't need to pay them a specific amount of money if you want to host it on their API. You don't need to do anything. You can just do whatever you want with this, basically. Just don't try and present yourself as them. I think Apache 2 basically prevents you from stealing their copyright, but it doesn't. It's MIT with a little bit more legal weight, is my understanding. And so there's the full model, but they also provided from themselves the NVFP4 version. So this is the pre-quantized version that specifically set up to work very well with NVIDIA chips and the NVIDIA quantization setup. So that's cool. It's cool that they've provided this. It's wonderful that we get that K3 white paper because we just don't necessarily know that we'll get that from other actors. This is one of the announcement posts, and basically what they're saying here is that it outperforms strong peers in its class, including DeepSeek V4 Flash. I included this because this did not last. They posted this, and the next day, DeepSeek V4 Flash was updated to improve on them. So that's a little bit of a spoiler for what's coming later. But yeah, this is kind of cool because he says that Inkling-Small began with an on-policy distillation from Inkling, which we talked about that on-policy distillation idea before. And that allowed it to catch up to Inkling very quickly. And then they ran 2 weeks of continuous RL. That's it. And produced a much stronger final model. It sounds like they didn't do the multi MOPD thing where they trained specialized experts and then distilled them back. It looks like this was just RL. But you can imagine where things are going to go in the future. Do RL experts and then OPD it back on. And then what's kind of interesting about this is that they describe this as feeling like just routine. Whereas with the previous Inkling model, it took a lot of effort. They had to set a lot of things up from scratch. They had to build their data pipelines. They had to do all that. What they feel is that this was kind of just like turning their model factory on and setting it to a smaller setting, which is pretty cool. It's kind of cool to see that they're getting into a cadence now where maybe we're just going to see more and better and faster releases from them. This was certainly a fast follow-up to their initial release. And this was kind of funny. Like, why not name it Shrinkling? I thought that was funny. And then what's cool is that not only has it launched, but people have already created optimized versions of this. So people took this and did a DSpark fine tune. DSpark is this new way of doing speculative decoding using diffusion. You start with the original model, do some fine tuning on it, and voila, you get this incredible fast speculative decoding thing where you're getting the exact same tokens out, but it's proposing like chunks of them at a time. It's proposing 4 at a time or whatever. And then as long as those 4 match up with the 4 that it would have produced, you can just output those 4 right away. And so using this type of a setup, which is great, the open source community can provide, they're getting 648 tokens a second, which is just insane. So this is a small model that's got relatively fast performance that the community has built fast speculative decoding on, and you're getting reasonably fast speed. Like, that's a fast speed. If you felt that on your agentic outputs, it's going to feel way faster than like the typical OpenAI or Anthropic models. You're getting like 50 tokens a second with that. So 650 tokens a second is going to feel just insanely fast, which is insane. It's great. It's incredible. This is the benefit of the open source community providing these types of thing. This is an incredibly exciting model because it's just so much smaller. It's hitting the same sort of heights on some of the benchmarks, and that means that you can do it cheaper, you can inference faster, you can fine tune faster. That's one of the things they really like. This is ultimately what thinking machines is about, is fine tuning. So they provided a model that's going to be very good and fast for that. So we talked about K3, which pushed up the capability frontier. We talked about Inkling-Small, which seems to match their previous capabilities, but at a much smaller model size. And then comes out DeepSeek V4 Flash at the end of the month. They said they were going to have some updates in July, and they waited until the last day of July, but they got it out there. But what is this? What is this? It's a massively upgraded version. If you look at these numbers, the old numbers and the new numbers, this was the previously open source version of DeepSeek V4 Flash. This is the new version of DeepSeek V4 Flash. This is the same model. It's actually the same weights. It's the same architecture. You could load up anything that you used in your previous DeepSeek V4 Flash, swap out the model weights, and you get this. And we're talking a huge jump from 61 to 82 on Terminal Bench, from 39 to 54 on NL2, from 38 to 76 on CyberGym, from 7 to 54 on DeepSui, which is like software engineering tasks, this is like what people really use this stuff for. Every single number we're looking at here, they've just done so much improvement on it. And I think it ties into a lot of what we were talking about in the previous two open source models. The faster you can inference, the more you can hill climb. And they have been hill climbing. So that's pretty exciting. Not only was it announced, but that same day, hours later, they released the model. This one is MIT licensed. It's the most open and permissive license you can basically ask for. And you can slot it in with all the other things. They also released themselves the DSpark. This is the efficient speculative decoding stuff that I was talking about that an open source lab did for the Inkling-Small. In this case, DeepSeek released it themselves. They've trained it themselves. So you're getting, this is the way of making it go very, very fast, and they're going to make sure that everybody has access to that. That is incredible. And if you look at it, it is 304 billion parameters, and we'll talk more about it. But also, right on day one, we had Unsloth create GGUFs. This means that if you have a computer that has a lot of RAM, a lot of VRAM, maybe you've got one of the new Macs that maybe you've got an M3 Ultra that has more than 128 gigs of RAM, VRAM, you could potentially run this. So as long as you have essentially 102, well, I wouldn't use the 1 or 2 bits. I probably wouldn't use the 3 bits. But as long as you've got more than 162 gigabytes of VRAM, whether it's unified or not, you can run this, which is crazy. So it's cool that Unsloth was able to create their GGUFs right away. And people have really been trying to optimize the performance on this, trying in a bunch of different configurations. So we've got the TinyGrad, which they have a setup with 2 RTX 6000 Blackwells. Those are 96 gigabytes of VRAM. So combined, you've got enough to run these things. And they're saying that they're hitting 245 tokens a second, which is incredible. Like 265 tokens a second, or 245 tokens a second, is probably like 5 times faster than you're going to feel like GPT 5.6 Sol. This is super fast. This is great. It's unfortunate that it requires 2 GPUs. It's just a little too big for one, but this is an incredible result. By the way, these TinyGrad things, I think one RTX 6000 Blackwell GPU costs about $10,000 by itself. So if you wanted to put together a system for yourself, not using TinyGrad, not using TinyCorp, you could basically buy this. That would be like $20,000 for the GPUs. You're going to spend probably, let's say, $5,000 for the rest of the system. So for $25,000, that's a pretty reasonable setup for a reasonably good frontier quality model. We're not talking like GPT 5.6 Sol Frontier. We're talking like GPT 5.6 Luna Frontier, and that's pretty impressive that you could get that for $25,000 and you're going at 240 tokens a second. I just can't think of any business that wouldn't be improved by having that type of a setup and not having to pay for any incremental costs. You're just paying for your energy at that point. Pretty impressive. But then also we have these DGX Sparks now. These are kind of like desktop computers. I don't know what they cost anymore, but it's like a very small GPU core combined with a decent amount of memory. I think they're 128 gigs of unified memory each. So 128 gigs of unified memory isn't necessarily enough to keep the whole model on one. So this is somebody who's they put together 2. They've got 2 DGX Sparks connected, and they're finding ways to split the model up and run it across both. And they're seeing about 100 tokens a second, 95.9 tokens per second. And if I understand correctly, they're not compromising by doing crazy quants or something like that. I think This is reasonably standardized inference. And it's all open source. You can download it. You can do it today. You can use it. However, a lot of people don't have 2 Sparks. They've got 1. And what this person has been working on is a way of smartly allocating what ones are on disk, what ones are in RAM, and then figuring out how to page those out properly, is my understanding. And they're not overly quantizing it. They're not like removing a bunch of layers. They're not destroying the model. And what they're seeing is that they can get to 59 tokens a second. Now, this is not 59 tokens a second for one user. They're sending like a bunch of things through this at once and using bigger batch sizes. This is like pushing it a little bit in terms of, I don't know what you'd actually get for a single agent serving. I'm not exactly sure, but this is pretty cool. And then somebody got it working with on their M3 Ultra. So using Dwarf Star, and they've got it running at about 27 tokens a second. This is, for me, my personal feeling is this is about like the limit of what you could use before it starts to get too slow for your own agentic coding use cases. If you're sitting there and like looking at the output, obviously if you've got like some background process using background agents, then you can push the tokens per second even lower. But for 27 tokens a second, that feels real time. That feels reasonable for an agentic coding workload. And so we looked at the official benchmarks, but let's look at the benchmarks from the different companies. This is an incredible leap from like a score of 40 to a score of 50. He is hanging up there with like GPT 5.6 Luna at max. GLM 5.2, which is a much, much larger and slower model at max. MuSpark, which is the best thing that Meta has released yet so far, at their highest setting. Like, it's pretty much right there with those impressive models at this point. And we're starting to get to the point in this class where you can do a lot of tasks. It's not limited to feeling like it's a small model. We're starting to feel like when you get to this level, you start to feel like this is a capable model that can really accomplish the tasks that I needed to do. And I think this is maybe one of the most striking graphs of the whole thing, where this is what you could kind of consider the Pareto frontier. This idea of like, for the cost, what am I getting out of this? And I think this chart was created before the Luna price changes, so that might shift it over this way in terms of like the cost. But look at how much more intelligence you're getting for so little cost here. And this is the same model. So this just shows you the power of post-training. This shows you the power of RL, really. Look at this as an outlier on this graph. If you can kind of like chart a line, like if you did a linear fit between Mimo v2.5 through to Claude Opus 5 Max, you'd get this reasonably good line that would kind of go through everything. Now, DeepSeek V4 Flash would kind of like push it up, but this new thing, these new Luna and DeepSeek V4 Flash 0731, this is going to not fit on that line. This is creating a new line. You should just look at this leap from 1189, same model, more post-training. Now we're at 1559. Again, right, trading blows with Luna, trading blows with Terra. Not too far away from Opus 4.8, frankly. GDP val is a very strong benchmark. I think GDP val was created by OpenAI themselves. Obviously, you're still not, this is 1559, you're not getting up to GPT 5.6 Sol at max setting. We're not there exactly with this Flash model, but this is a Flash model. This is a fast model that you can run on one DSpark, or one DGX Spark. So it's really not just the capabilities that are impressive here. It's the capabilities at this cost. It's at this speed, at this accessibility level. It's pretty much impossible to think about an end user buying the hardware that it takes to run Kimi K3. But I could run out tomorrow and buy the hardware. It would be expensive. You buy a car and you drive it for years. And I think that we're getting to the model class where you could buy a car level of computers and and run it for years on this stack, and you just know that this is going to get better and faster at the same capability, at the same inference class. Yes, it could be a lot better, but this is no slouch of a model. And that was then. This is the live actual data as you look at it today. So has anything changed? I don't think so. This is still by far the best cost per task. Interesting also to look at the tokens used for the task. It uses more tokens, but they're so much cheaper. But it is important to note that it does use a lot more tokens for its reasoning. 37,000 tokens in reasoning versus Kimi K3 using less than 2,000. So that's a big difference. So this is something they can still push on. Imagine if we could get this down to there, to this area. That would be incredible. But what we do see in general is that with smaller models, they need to make up for their lack of size with more reasoning tokens. That is just something we generally see. It also could be something to do with the training process, and it could be that like with better post-training, you could push that down. For example, like GPT OSS 120B, we know that OpenAI knows how to post-train their models to be efficient reasoners. And even with theirs, they're hitting these high numbers on the amount of reasoning tokens. I've done a bunch of experiments with like a 4B model, the Qwen 3.5 4B model, and I've found that in general, it requires tons of reasoning tokens to just get to the right answer. And if you cut it off early, it gets wrong very quickly. So anyway, something to know about. But even still, even with the higher number of tokens, it still costs so much less than all the competitors. So we are spending more tokens, but we're getting, even though we're still hitting low costs. So that's good to know. Now, the code arena. We talked about before how K3 had the top score when it came out, and then Opus 5 just recently surpassed it. Where does DeepSeek V4 Flash sit? It sits right there. It sits up there with GLM 5.2. So while it's not hitting these highs that K3 has and Opus 5 has, it's hanging in there with the other open source models and the bigger ones. This 5.2 is a much bigger model. You can just see the Pareto frontier, like this pushes out. It's such an outlier in terms of the capability you get for the cost. Like if you look at Laguna XS, this is an open source model. These are all the open source ones, right? I guess this is the one non-open source, but with Kimi K3, it's hitting these highs, but it's also relatively expensive. And as you go down the price curve, like we're talking like 20 cents here. This is the next closest open source model. Like this is a very good open source model. But DeepSeek V4 Flash is just so much better. And then here is the Simon Willison Pelican test. And as you can see, he got on default reasoning mode, he got a pretty bad one. Not so great. This isn't great. But he bumped up to the high reasoning mode and got a lot better. This is night and day. So this really goes to show you the power of the reasoning modes and how many more thinking tokens it uses and how much that can affect the quality of the results. Also, this looks like it's been post-trained. Like, honestly, I would be surprised if there wasn't something in the training data that created, like, this is a really good Pelican, in my opinion. It's not perfect. It's like, there's some weird stuff, but this is a pretty good Pelican. So the other thing is, there's a bunch of free providers of this. OpenCode Go has a free version of this. So if you download OpenCode, you sign up for an account, you have free access to, for a decent amount of tokens, to this DeepSeek V4 Flash model. Also, Hugging Face themselves opened up a endpoint. It's a free model. You can use it. You can connect to it. You can. I think they might still have it up, but this is the one that I'm not sure about. This one might be down by now. Klein, they're another coding provider. They have provided a free version of this for you to try out. So everybody's trying to get you. Also, I don't know what this ZenMux is, but they also provide it for free. And they can afford to do this because it's just as few GPUs they have to spend on it. It's not some big hardware layout. They can just repurpose a couple GPUs and say, hey, try our service for free. That's cool. So this is a really exciting release, a very impressive. So between all three of these, we've got K3 pushing up the capability frontier. We've got Inkling-Small proving that like a Western lab can do all these same things and release it open source, and it matches their larger model. And this is just an indication for where things are going. And they've got their model factory going. Like that felt routine to them. And then now we've got DeepSeek V4 Flash, which pushes up the capability, cost, accessibility frontier. So that's these are a really cool set of open source releases just in the last 2 weeks, really. And really, in the last week, we've got these latest few. So this really, I think, even just in absolute terms, these are great models to be using. Each one of these you can use today for tasks that you've got today. But I think what's more interesting is to look at the trajectory of these models. These smaller models that are able to post-train faster, these model factories, they're becoming more routine. They're able to distill from their larger models using OPD, MOPD on their existing models and match them and improve upon them and go beyond. So this is just, I think, an indication of where things are going. You're going to get faster, better, more powerful models over the course of the next year. I don't see this slowing down. What will be interesting is this graph, where as we push on these other capabilities, as we're trying to extract more and more of the coding capabilities, the terminal bench, we're trying to basically keep these fixed or push them further. How can we keep, like, where does this go? Does this go down further? Do we sort of steal capacity from the factuality and from the world knowledge, in order to sort of reallocate it towards reasoning and coding? Or are we going to find capabilities and ways of sort of like making it better at all of them? And will we be able to push the accessibility factor even lower? Like, what if there's a 32 billion parameter model, or a 16 billion parameter model, or a 4 billion parameter model? How far can we push that like lower barrier, and maybe sacrifice some of the world knowledge and some of the general knowledge, but like how much can we retain these performance and maybe even push further on some of these useful tasks? So that's, I think, like what's really interesting to think about for the future.